Okay, we are live.
Hi, everyone, and welcome to the third of the bi-weekly community calls. We're going to try out a new format today. I'm going to go into that more soon. But the general topic of today is dynamic proof of location, and we will talk about the GeoPickle, which is a setup we've built at the new lab for simulating a testing environment for zone anchors. And we're also going to talk about a new functionality that is added to the phone map soon, which is a heat map view for signals. But before that, we're going to kind of switch it around this time and start with the questions first. We have some questions that were added previously via the Google form, but we also encourage people to ask questions directly into the YouTube chat window here, and we'll make sure to answer them directly. And through this, we want to kind of allow people that are joining now to not miss the first part and start with the questions as the first block. So let's get straight through the questions. And whoever from the phone team who feels like they have a good answer for this, please chime in. So the first question is, when is it coming to Canada? And I think for that, so the phone map is already functioning in Canada. Regarding setting up zone anchors, which is probably what the person asking the question is getting at, you probably have to wait some time. What we've communicated before is having testing environments up by end of the year. That seems accurate. Is there someone else that wants to chime in from the team?
No, that's definitely the case that we're working now. So to recap, we're going to have most of this call on new ways to understand signaling and the GeoPickle, which is a way to simulate zone anchors in experiment in all different kinds of transport layers. So by that, we mean different kinds of radios. But with that, we are working to get our software running fully on different kinds of radios. And when we have that, the goal is to make that available to all community members and have their own initiatives to set up test nets where they locate. So if you're in Canada and want to participate, definitely keep up with our progress, and we'll make that available to you as soon as we can. And we'll be publishing, more detailed milestones and roadmaps as we, make further progress in our development.
Okay, there's another question which is about, this is a general question to the team. Is it getting harder or easier to conquer the task at hand? Which I guess is about, as we progress with this, is it increasing difficulty or not?
I can speak to that in a way it's almost getting simpler due to the explosion of growth we've seen in the Ethereum ecosystem over the last year. Even just from DevCon in October to ETH Denver that just occurred last weekend, the kind of progress being made in ancillary projects, whether that's user experience, ways to make starter kits, but more importantly for us on dynamic proof of location, the progress being made in scaling solutions, plasma, counterfactual verification. There's actually now well-funded teams working on all of these problems, and we'll be able to utilize these tools. So in that sense, there's more of a shared ecosystem that's developing that we can leverage in our development. So of course, it's still a challenging endeavor, but definitely over the last year, from when we were conceiving and writing the technical white paper, a lot of the things we wrote about have been built out by other teams, and we'll be able to utilize them in the test setups in the GeoPickle, which Christopher and Ilya will speak to a little later in the call.
Then we also have 3 questions that are similar in terms of that people are eager to set up their own zone anchors, and regarding a timeline for the specs. And then also someone was asking how to set up their own GeoPickle. So some clarification surrounding that might be good.
So what we're going to have most of this call be about is the GeoPickle as this kind of test server simulation environment. And that allows us to basically test all different versions of the timesync protocol with different parameters. There's not necessarily a reason for you to want to build your own, but maybe there is actually, because it's likely we may release specifications around the actual software prior to get people to potentially test them in their own setups as well. So that's one thing you can look out for when the actual versions of the software being released, and we can have these virtual test nets if other people want to set up these kind of simulated zones. But it'll take us a bit more time to give specifications on which hardware we finalized on and the ways to get that software from a simulated environment onto actual devices. So we're doing bi-weekly community calls, kind of switching on and off on the foam map and the dynamic, and we'll probably have much more progress and timelines to share by the next dynamic proof of location call. Also, for anyone just tuning in, we're kind of just starting the first 10 minutes with a general lobby. So if you've just joined, please feel free to chime in with any questions in the YouTube chat. We're going to hang out for a few more minutes before we get started on the presentations.
So talking about that, there's another question coming in from Trenton about will foam be considering counterfactual plasma for implementation in the network?
Yeah, the answer is yes. You can see kind of a sketch of those ideas in our technical white paper. But now with this GeoPickle setup, our devs will speak more to it, but it allows us to also run like plasma operators and simulate those kind of things on the GeoPickle. And we've been spending a lot of time recently investigating counterfactuals in how either zones can speak to each other in state channels, but also the idea is to really utilize that tool in the verification so that off-chain computation can happen and the proofs are posted back to the chain and they can be verified in a counterfactual way, which basically means to post the answer, you also post a big bounty of ETH. And if somebody wants to prove you wrong, they can spend that amount of Ether to run the computation, but that would probably be less than the bounty there. So we are actively investigating plasma operators as well as counterfactual, and also by extension, we're utilizing Tendermint consensus on those chains. And another way to connect to a root chain instead of plasma may be the Cosmos-based IBC protocol. And so we're really open to all of these, and this kind of test setup that we're going to be diving into really gives us the flexibility to test all these different kind of technologies at a very low cost in kind of realistic scenarios.
Okay, we have another question coming in from Emily Davies. What do you guys see as the minimum area of coverage mapping that will be your critical mass? And I guess I'm not sure if this means for the foam map, so for static proof of location or for dynamic proof of location, but I think given how hard that is to answer, yeah, maybe I would, Ryan, do you have an answer for that for maybe zone anchors or?
Yeah, I'm not sure if you're referring to the foam map. So what's the kind of critical mass of points? I think that a few kind of locations already kind of start to appear like they're past some sort of threshold of being really filled out. I know that because we did the campaign in the Dumbo Brooklyn area, that's really looking like super fleshed out. That's an area I live in, so you can kind of see that most of the businesses I know exist are actually there. And there are a few other cities that kind of hit that point where all the most notable locations are there. But how to measure that critical mass, I think, is going to be contingent on how the map is being used. And so once things need to reference that registry and want to look at geodata on-chain instead of off, we'll be able to better understand what are the needs of those applications and have a better way to quantify if the amount of data there is sufficient, or is there a new mechanism to increase demand once applications need it. So we know right now that a lot of these Web3 technologies, including foam, are a little bit floating without the context of the apps, more as infrastructure and protocol. So how do we actually measure what is critical mass? We need the context of what are the users, and that's something we'll be keeping a close eye on and working with. When it comes to critical mass of the zone anchors, if you're using some of these low power radios, you can see in other communities, for example, the Things Network, which is a community of LoRa users that use the LoRa WAN MAC layer. Multiple cities kind of have maximum coverage. The radios can go up to 15 kilometers, probably more like 5 to 3 in an urban environment, but it doesn't really take that many. You can look, some have 10, some have 30, some have 50 to actually get full coverage of an area. So that's kind of easy to calculate. What is the maximum threshold you need to cover an area? But it gets a little bit more nuanced and complex when you're thinking how many do you need to actually sufficiently run the time sync protocol. And that number is going to be changing based on each kind of city environment or rural environment. And that's why to finalize that protocol, it's going to be so contingent that it is an actual grassroots efforts where teams can organize to run the test nets and report the kind of results in their environment so that can inform the final parameters of the protocol. So we can, just to rehash, we can calculate, how many radios you would need to theoretically cover an area, but that doesn't actually mean it's enough to accurately run our protocol. And for that, that's why it's going to be so crucial for us to support community members who want to roam testnets.
Okay, I think that's all the questions we have for now, and we've hit the 10-minute mark. So we're going to start with the main part of the call, which are the two presentations. First, Jens, one of our developers, will showcase a new functionality that will be built out into the full map soon, a heat map for signals. So with that, Jens, I'll give it over to you.
Yeah, hello everybody. My name is Jens. I'm a senior developer at Foam and part of the developer team for the Foam TCR map. And let's start by sharing my screen. Okay, can you see my screen? Good. Okay, today I'm going to demonstrate a new feature of the map we will have within next release. This feature is called Signal Heat Map. Before I'm going to go into the details of the new Signal Heat Map, let me take a minute to talk about what a heat map is in general. So if you're looking around to find a definition of a heat map, you will see that there are very different definitions. And the reason for this is there is not just one type of a heat map, but very different types. And here's a definition which describes exactly what we are doing with our new signal heat map. And the definition says a heat map is a visualization used to depict the intensity of data at geographical points. The important thing is the intensity. And for us, the question is, what is the intensity of a signal? By the way, this quote comes from the developers portal of Google. And but we don't use Google, we are using Mapbox, by the way. So back to the question, what is the intensity of a signal? To give an answer to this question, let's move over to the map. I'm running here the map on my machine. You see it here by localhost, but I have connected it to the mainnet. That means all the data we have here at the map are the real data you will have at the map foam.space website. So let's grab any of these signal to see what kind of values we got. So the first thing we see is the ID. This ID is not so interesting to get an intensity. The next value we have is this stake value. This sounds very interesting. The other values are the position of this signal. This is the geohash, the physical address, and the longitude and latitude. But we don't need this to get the intensity of a signal. And the last value we see here is this radius of the signal. And that sounds very interesting too. So what we have done is we have decided that we are using this stake value to get the intensity on the heat map. But behind the scenes, we are doing some computation and interpolation depending on the zoom level. So even we are using the stake value for the intensity, it's not really just the stake value, but also some calculation behind the scenes. And to see what the difference is between the signal's intensity, we are using a color range. And the color range looks like this. It's from top to the bottom. The colors gets from blue up to the yellow. And it means the more a signal has been staked, the more the color gets from the blue to the yellow. So if you have an area with some signals, and you have a signal, let's say for about 10 foam, it will mix more into the blue area. And if you have another signals with 50,000 of foam, then it will get into the yellow color range. So, and what about the radius? As I said before, the radius is very interesting for us. So even if we didn't decide to use the radius of a signal not to calculate the intensity, but we use this on another part to draw the heat map. And we are using the radius in the matter that the larger the radius is, the larger the area of a heat map. And the same as we have done with the calculation of the intensity, we are doing some computation and interpolation depending on the zoom level. So let's see an example. Here we have two signals in the area of Sacramento and Davis. The signal in Sacramento have 15 kilometers radius, and the another signal is 2 kilometers. This is this one. Here you can see that the heat map, it's drawing depending on the radius. The Sacramento area is larger than the area of the heat map in the Davis location. So now it's time to analyze some real data, and so we are going back to the map. To start the signal heat mappers, you have to go to the lower right-hand corner to the map layers button to click the button heat map of signals, and then you will get the signal heat map on the map. If I zoom out, and I have to wait a little bit to get all the data, here we have a nice example of different kind of signals in the area of San Francisco to the area of Sunnyvale and San Jose. As you can see, we have in the area of San Francisco a very yellow area, which means we have here very high staked signals. And the same we do have in the southern area around San Jose and Sunnyvale. And in between, we have this connected area which goes into the blue color, which means in this area we don't have the same higher staked signals as we have in San Francisco and in this southern area. So let's zoom in to see what does it mean we have here more blue colors by just checking one of the signals. Okay, this signal has 50,000 foam, that's not bad. The other one has the same value of foam. And if I scroll into the area of San Francisco, I have to load a little bit. So I have to check the same signals in this area. This signal has just 10. There's also 10 foam, 10 foam. Oh, here's a 20 foam, but not 50,000 foam. 20 foam. So the question is, why do we have here more the yellow color than in the other part in the south? The reason for this is that we have in this area 1 point. This is this guy. This is staked with 190,000 foam, and that means if you have an area with very less strict signals, but one signal with a very high intensity, the color gets into the yellow color, comparing to the other signals in the south. So the next question is, why do we have this bigger radius here? It's getting blue, but the radius is bigger than in this area. So we can compare this by selecting again this signal here, and we see, okay, the signal has a radius of 1 kilometer, and this signal has a radius of 3 kilometers. And if we are going back to San Francisco, and if we are check the signals here, we will see, okay, this one has 2 kilometers, this one has 2 kilometers, this one has 2 kilometers, but this one here, what, this one? No, this one. Okay, yeah, has 15 kilometers. And that's the reason that this area in San Francisco gets a bigger radius than the other area around. So yeah, I hope you get a feeling about how to interpret the heat map and how to analyze the data. Just keep in mind, we are using the radius, but also the staked value. And I hope you enjoy the new feature. And yeah, let's have fun to scroll around the map and check out the new feature with the new release. That's all from my side.
Thank you very much, Jens. I think that was a great overview. It's going to be really interesting to see what we can find on the map. After checking it out with the new mainnet data, there were already some interesting patterns and kind of signal clusters, which I hadn't seen before on the map. So it really also helps with navigating through previously unseen kind of signal clusters. I think it's time now for the next part of the call, which is an introduction to the GeoPickle. If someone wants to say something before that presentation starts, otherwise I give it over to Christopher and Elliot. Christopher and Ilya?
Hey.
Hey.
Yeah, should get those out. Yeah, thanks for that presentation, Jens. Okay, so today we're gathered here around our latest gadget. You can call it maybe unboxing. It's an unboxing video. It's the first unboxing, but not the last. No, but so we're actually sitting in an awkward corner of the office because this thing, although it has wheels, is pretty annoying to move because it's connected to the only place where we have Ethernet in the office. So we've been working on this the past couple of, well, I think almost a month now, and we call the rack this unit. Yeah, let's go back to it. We call it the Geo Pickle. There's a few puns in there. Maybe the most important part of the pun is that it consists of Raspberry Pis. So we're currently housing 12 Raspberry Pis, but it readily allows us to put in another 28, totaling 40 Raspberry Pis. I'm going to also share the screen here. Working? Okay. Why are we using Raspberry Pis? Well, so it has a few advantages. Like all of our prototyping with the radios is utilizing a Raspberry Pi to this point, and most of the development boards that you can get from different radio chip manufacturers are compatible with the Raspberry Pi. So we're using that in order to build a test environment that we hope overlaps as much as possible with a physical test environment that we are building in parallel. I have some notes. You want to show this maybe in the meantime?
Yeah, so hearing myself.
I know.
Anyway, so you guys probably know what a Raspberry Pi looks like. Nothing new here. Run-of-the-mill, off-the-shelf Raspberry Pi 3B+. We put in a few little heat sinks on it because apparently these things tend to thermally throttle themselves very quickly unless you do. And as you know, these things are $35 a pop, which is, as you scale out to this, A, dirt cheap for the compute, and B, they're also really low power. Like, the amount of compute you're getting out of this for the power you're putting in it's a pretty good density. But what you end up doing is you can get a board like this. One of these is one of the blades that goes in there. So there's 10 of these in total for each 7-rack unit GeoPickle, and they're not that thick either. So we can actually put 2 sets of these into the same set of 7-rack units, and that just fits 4 Pis. They get really cleanly powered. They're all networked together. End up going into that switch there, which we'll get into in just a second, which effectively allows us to simulate basically any transport layer, which is, you know, in the real world, it's going to be radio, but there's only so many radios you can stick in a small space like this. So, Chris, you want to?
Yeah. So the way we think of this is basically as a test net, or multiple test nets, if you think about it. So one of the kind of issues with Raspberry Pis that, you know, maybe if you've used them before, you're kind of familiar with, is that although they're very cheap and they're very sort of easy to use, it gets really time consuming to either network into them and change their, you know, Linux distribution, or just generally communicate with more than one. And so what we've done to lengths here is to make a SD card less configuration. So these Raspberry Pis actually don't need SD cards. We can use them for storage, but instead we're utilizing network booting using what's called Pixie boot. And so in addition to the Raspberry Pis, we have a switch, but also just a sort of like a normal server that allows us to very quickly recompile both binaries or the Linux kernel, or we can even do without a Linux kernel and boot straight to the some ARM-aware firmware. And whenever we reboot the Raspberry Pi, it simply communicates with the network that it needs its firmware, and it gets that from the server. And because of the way the network is configured, the server can then tell or give, for example, different Pis different softwares. That could amount to being uniformly the same software, but have slightly different parameters, such as host names. That lets us distinguish them. But it could also, for example, let us run a real-time kernel on half of these and a non-real-time kernel on the other ones, and then we can see the difference in performance. And so it's really important to not be bogged down into not wanting to run certain kinds of tests, because it would take you even 5 minutes to do the work manually. Like, so what we're hoping that we created here is a fully automated test environment. Which also is important because we have, actually most of our development team is remote. So this also allows us to collaborate on this project with everyone. So Ilya, you mentioned that we have sort of like a virtual transport layer. So when we mean transport layer, it's a very general term, right? Like the Raspberry Pis needs to communicate with one another. And so what we're building on the radio side is a transport layer that utilizes currently the LoRa chip. But because we have this very expensive switch, or used to be expensive, we can basically create a very configurable virtual transport layer. So one of the kind of neat things is that when the Raspberry Pis talk to each other, we're only allowing them to ever do broadcasting. That means that any Raspberry Pi does not know any other information about the other Raspberry Pis. The only way they can infer information about the other Raspberry Pis is by sending broadcast packets and receiving them. And the way we configure what Raspberry Pi can talk to another one is through the switch. So that lets us build quote-unquote software on the Raspberry Pis, or more universal, and let us set up all the different configurations and run the different experiments with different parameters by just configuring the router or the switch.
Really both. You can actually start getting into more interesting setups where, so as it's currently set up right now, and in the demo we're going to show in a bit, just every one of those blades is its own zone. They can only talk to each other, but yeah, because we kind of have this like enterprise grade switch and router setup, we can also start doing interesting things like setting up multicast, where I could say one of those Pis can talk to all the other Pis in the zone, but its messages can also be broadcast out to a single other Pi in another zone. So now you could start checking things like, are zones contiguous? Can you like have connectivity between them? What happens in scenarios like that? And yeah, ultimately, as Chris said, the real interesting thing is you can basically set up any topology and run whatever kind of tests you want against it to see if it makes sense, if it works. And that in turn ends up driving like other parts of the whole phone network to implementation.
Right, if you can switch to my screen. Showing? Yes. Okay. Well, so just to sort of like, I try to make a few diagrams here. So if this very rudimentary diagram corresponds to our current setup, sort of the physical layout of the Pis, you can see that we're naming them sort of zone 1, node 1, zone 1, node 2, all the way down to zone 10, node 4. So that's kind of the physical layout, but what it then lets us do, as I'm going to illustrate sort of like the very rudimentary virtual transport layer, right? Like, so here we're in zone 1, and we are placing virtually the zones at a distance, can't do the calculation off the top of my head, but in this configuration. And we can then use in the router, the switch, introduce packet delays between the different nodes. So like node 4 and 3 has X nanoseconds delay. Node 3 and 2 has Y, and corresponding on the other side of the diagram, which also induces through, triangle inequality, the minimum distance traveled on the diagonals. And so by putting these delays, pure packet delays, on the switch, we can effectively emulate a sort of like a rectangular configuration of zones. So we can obviously do a lot more interesting things, such as introducing statistic or sort of delays according to certain statistical distributions, or we can introduce anomalies so that the square actually doesn't match up and so on. Another example that I was trying to sketch here is that you have two zones with mobile beacons. The mobile beacons here, again, can be represented by a Raspberry Pi, right? Because what is a mobile beacon? It's just a node that can receive sufficient packets from the zone to determine that they're within it. And we configure that simply with the switch. And so we can then start running experiments according to these configurations and see, for example, purely like, does mobile beacon 1 and 2 see the same things? Are they able to infer the same information from purely the packets? I think that was the only diagrams I made, so we can turn it off. So I mentioned, you can see on the device that we have the switch, the router. We also have the server. Because we are not wedded yet to our sort of layer 2 infrastructure. We want to run experiments on that as well. We can use this server to, for example, act as a blockchain node, an Ethereum node. We can run a plasma operator on it. We can sort of lift all of the heavy blockchain computation from the Pis onto the server if that's what we need to do. We can, of course, by just changing the binaries on the Pis, allow them to run that part of the software themselves. And so that way we can easily benchmark what is the difference between having an Ethereum node or some other kind of blockchain-aware service on each of the Pis versus having a centralized one on its own basis, or maybe one that would amount to a node being able to talk to the internet. I guess another just point that the server fulfills here is that so we want to be able to separate sort of the logs produced by the zone anchors on the blockchain, which is some kind of aggregate of the messages being passed around. But we also want to do very aggressive logging, sort of just like normal logs onto the server. And these logs fulfill a different kind of role because we eventually or ultimately want to run a lot of statistics on the simulations. So we want to. So the time synchronization protocol that we're using has a bunch of different parameters. That is, on the one hand, tied to sort of the clocks and the characteristics of the Pi themselves, but it also relates to the transport times. And so we need to be able to fine-tune these parameters. And what we want to do is basically run the whole parameter space automatically and be able to, from the logs, be able to infer the performance of the zones themselves. And so that's why we have this server. And we envision that a lot of the software we're running is actually going to be sort of like an analytics type of software. I have a few examples. I feel that I probably talked about them already, but I wrote them down. So just finishing up before we actually go into a demo. So some example scenarios that you can run on this machine is that you can run 10 zones simultaneously using different parameters but talking to the same blockchain. So now you can see, by only looking at the blockchain, like what are the performance characteristics of these different zones. Ilya mentioned we can overlap or partially overlap zones and see how that affects the performance of the zone. We can introduce errors. This is important for us to sort of test the Byzantine font tolerant aspect of time synchronization protocol, so we can drop packets, we can delay them, we can actually introduce malicious packets, etc. And importantly, we will then want to be able to infer or correlate on the log side of things the errors that we've introduced. Another important part on the higher level of the stack is that we know that we can generate presence claims. We want to basically find out like what is how many presence claims per second can we generate, assuming that we have a perfect transport layer that acts optimally always. That will tell us at a bound, at least using the current iteration of the software, that we can then expect and compare against when we're running this over radios. Yeah, and I think I mentioned earlier, we can then connect this to different blockchain solutions and see if that, which one would match our performance best by sort of separating that layer by simply running it on the server or not, and not having to be affected by the radio. I think that's it.
Yeah, I mean, I think there's one under-stressed point here. It's just how totally modular this thing is. I mean, you've seen the Pis are just off the shelf. Something goes wrong with one of them, it starts letting out the magic smoke. We can easily plop another one in. We decide that, hey, switch is a bottleneck for whatever reason. Like, we can rip it out, replace it with like an InfiniBand fabric or something crazy like that if it turns out we need to. So I think that's just one of the more subtle points of this is that, yeah, it's running on Pis, but the whole point is that you could basically mix and match any sort of configuration you want.
I have a question. So where's the operating system if there's no SD?
So these are actually being booted over the network, something called PXE, or Portable Execution Environment Net Booting. This is actually the same way that if you're like a large organization and you just got 1,000 new computers in, you need to set up, an operating system and stuff on them. Obviously, you don't want to be sitting there, keying in the setup for Windows 1,000 times. So what you actually do is you set up what's called a PXE server, and you tell all those, well, you probably tell like whoever you bought those computers from, hey, make them net boot out of the box, which is actually what these Pis do. If you buy a new Raspberry Pi, put it on a network that has PXE booting, it'll actually just try to boot from that before it even hits the SD card. So the way that
It
it's
basically
set up,
pulls the image.
Yeah.
It pulls an image that currently contains a Debian,
mm-hmm.
but it could be another.
Yeah, so when it starts up, it sends out a packet, hey, give me an IP address, give me all that lovely stuff. The server actually sees that, and it says, hey, this looks like a Raspberry Pi. Because it's all going through the switch actually injects some metadata, like which port is it connected to, like what kind of, what's actually on the other end, and we can use all that information to decide what the Pi boots, whether that's Linux, whether that's a different configuration, or even if it's some sort of bare metal firmware that's not even related to Linux and just has just enough stuff to run a zone anchor over this architecture, which is, yeah, lovely stuff. Just all, I don't know, I get excited about this kind of thing. Anyway, I'm about to go into a screen share, so I'm actually going to show you one of the simulations that we can run. This one's super rudimentary. This is actually, you guys remember the ME demo from the last time? The time before, the community call before last time I was on. You saw me running a simulation of a zone on my computer. So we're going to do the same thing, just using the rightmost 4 nodes of the GeoPickle. So all these guys are zone 10, and as soon as I start the demo, you're actually going to see some windows of the Pi at zone 10, and one node on and one window on the server itself. So the 4 Pis are all going to run their own individual instance of the time sync protocol, only being able to speak to one another. While all we're going to do is we're going to kick it off, and then we're just going to watch the network traffic going through that zone. I just need 1 quick second to set it up. All right, let me start the screen share. If I screen share, am I going to be in that mic or in this mic?
Mute yourself.
Mute myself and start the screen share? Gotcha. Share your entire screen. Oh boy, I hope I have nothing incriminating here. All right. So over here, that's readable, right? All right. So these top 4 windows are 4 Pis, each of 1 blade. That's the zone 10 blade. Through the name, you can see Z10N01, so zone 10 node 1, zone 10 node 2, zone 10 node 3, zone 10 node 4. And they're running some upgraded, new and improved version of the ME software that you saw last time. And what's going to happen is they're going to start up. They're actually going to do a rough time synchronization using some classic stuff called NTP. And the reason for this is just for the sake of precision in your measurements, you kind of want the sim to start at roughly the same time. So you'll actually see that it did an NTP correction. Each Pi is going to have a slightly different one. So this guy was 23 milliseconds ahead of NTP time. This guy was 21. This guy was pretty good, 451 microseconds. That's actually impressive, all things considered. This guy was 36 ahead. So they all have some initial parameters set for the network for this particular simulation we're about to do. And down here on the bottom, I am going to tell the server to tell the rest of the pies to start the sim in exactly 5 seconds. So as soon as I hit this, server also does an NTP correction. Notice it found the Sentinel, and in about now, they're all going to start running the time sync protocol, sending out messages. And you can see, like, say this is node 2. Every time it spits out a sync message, everyone's like second box has like a message received. And what's actually neat is we start that's not good. I actually have this copy pasted somewhere. Yeah, so if we start, wow, okay. I should know this off the top of my head too, that's the sound part. But yeah, so we're gonna run a TCP dump just to sniff the traffic going over the Zone 10 network. And as we do that, we're gonna find, actually I can go to a different port. We're gonna start seeing that these guys, this are all different zone anchors, just broadcasting out messages saying, hey, I'm taking, this is, these are all elements of the time sync protocol. So, yeah, that's where we're at so far with it, but I think going forward, yeah, really soon this is going to have like dynamic configuration as well, where basically we just tell the Power Edge, hey, run like 20 different simulations, tweaking this parameter set, see which ones work, which converge, which crash. Yeah, just really exciting stuff. I actually can't wait to show you some of the stuff we end up discovering too. It was a ton of fun today. Awesome. All right, that's all from me.
Thanks, guys. Is there something more on the GeoPickle side? Otherwise, I think we're at the end of this call. That was very nice, and it's very nice to see how it's moving forward. Okay. So I think both thank you to Jens, Christopher, and Ilya for the demos. We will be launching the heat map soon. You can expect more write-ups and more of a deep dive into the GeoPickle soon as well. There will be another bi-weekly call in 2 weeks, as the name says. I'll be linking the Google Calendar link to sign up for our community call calendar in the chat window here, so you can sign up for future calls. And I think that's it.
Yeah, I just wanted to add, well, one, thanks for everyone for participating or joining, but in the next release coming next week, along with the heat map, we'll also have the challenge and point notification email system that we previewed in the last community call. That's currently on our testnet and will be pushed next week. And also next week, for those of you in our community, through the discourse, we'll be launching alpha testing of the new leaderboard feature to solicit feedback and see how that's going. So we've built out a leaderboard in collaboration with Blockalytics, which is nearly done for this stage. So we look forward to sharing early access to those in our community. Always feel free to start a new thread or reach out with any questions, and see you guys on the next call. Thanks, everyone.
Thanks, everyone. Have a great day. Bye.